Okay. So accretion can dominates the X-ray sky, and it can happen in, let's say, in two ways: through supermassive black holes, so in the active galactic nuclei, or in X-ray binaries with a difference of 6 orders of magnitude or more in mass. So X-ray binaries come in essentially two flavors. There are high mass X-ray binaries where accretion mainly occurs through the wind of the massive star, and accretion in low mass X-ray binaries where it happens through an accretion disk. High mass X-ray binaries are, of course, related to high mass stars, so they are essentially a young population. So when we look at them in the sky, they are essentially all along the galactic plane. The most updated catalogs show us that there are around 150 fully identified high mass X-ray binaries. And when we look at the low mass X-ray binaries, well, they also are in the galactic plane, but they also are essentially more condensated in the bulge, because they belong, of course, to an older population. In order to have a low mass X-ray binary, one needs to have an evolved low mass star as the companion of the compact object. And the most updated catalogs teach us that we have identified more than 300 low mass X-ray binaries in our Milky Way. So after this brief introduction, let's talk about what is a low mass X-ray binary. So essentially, there are, of course, binary systems, and they consist of a compact object, which can be either a black hole or a neutron star, and it needs a stellar companion. The stellar companion is usually an evolved dwarf or giant star, which is already overflowing its Roche law. And so part of the material has to start to escape from the star and forms, due to the conservation of angular momentum, it forms an accretion disk around the compact object. And this accretion disk, the matter in this accretion disk heats up and because of viscosity, and it heats up to temperatures of the order of the million of degrees. So it shines essentially in the soft X-ray band. So when we look at the spectrum of one of these sources in X-rays, we find always a soft or thermal emission coming from the disk. And because also in the innermost regions of this accretion flow, there is also another component called the corona, which is made of a cloud of hot electrons. And these hot electrons produce inverse Compton emission because they inverse Comptonized the soft emission from the source. And they produce a hard X-ray emission, which dominates in the around 10 kV band. So these sources also are also important in other wavelengths. In the radio band, they usually are detected because they also emit a radio jet, and also in the optical and infrared bands, there are signatures because of the synchrotron emission from the jet, but also from signatures from winds, which are very, very important and give a lot of information about the source. So when we go to, I wanted to have a proper slide about the work that's been done at IAC. As you can see here is a bit of the history of the discovery or detection of the first of all the black hole low mass X-ray binaries. So now I'm focusing on the low mass X-ray binaries who have a black hole as the compact object. And you can see that the first detections came, of course, at high energies in the X-rays. That's where the name comes from. And as time progresses, we've been collecting a lot of sources, more than 70 actually. And you can see in the blue part or here in the green part, all the dynamical masses, so the black holes that could be confirmed through the measurement of the dynamical mass thanks to optical observations. And you can see the impact of different telescopes. Once we've had telescope 20 years ago of 8 meters, so big telescopes, we started to have the possibility to measure many dynamical masses. And the reason why we discovered these sources following this trend is just simply because most of these sources are not persistent, but they are transient sources. So once they go into outburst is where we can detect them in X-ray. And then we start to study them. So after looking at all this family of black holes, we have made somehow a picture of how they evolve. And the most simple way to put them all and try to understand them is to create what are the so-called hardness intensity diagrams, right? So hardness is the ratio between the brightness in a hard X-ray band and a soft X-ray band. And here we can plot the full intensity of the source. So what we find is that sources start here in quiescence. They go up through this branch with a high hardness ratio. So they are essentially hard until they saturate at a certain brightness. And they start to transition to a softer state here. Then they go down, and then at some point they transition back to this hard state. So what essentially happens here is that there are essentially two different states. One is the low hard state, where the emission is essentially hard. As you can see here, there is a lot of hard emission, not too much soft emission. And what is happening here is that essentially the Comptonization component is dominating the high energies. And in this particular branch, there is not only hard emission, but also a lot of variability at different timescales. So there's high variability. And on the contrary, when we go to the soft state, the emission becomes very soft. You can see here the spectrum. There is a big contribution from the accretion disk and little contribution from the Comptonization. And then also the variability drops a lot. There is almost essentially no variability in that part of the diagram. Okay, so through the history, once this HID diagram was made, and once a lot of sources started to populate it and show this kind of the same shape, many people started to work about ideas of how what was the mechanism behind this evolution. And there are many ideas floating around in the literature. And however, after about 50 years of studies, there are many important questions that remain open. So this is some important message. That first question that we always discuss when we are talking about these sources in the community is whether actually the accretion disk reaches the innermost stable circular orbit or not when it goes through the hard states. Also, there is debate about what is the nature of the corona. It's unclear whether the corona is just made by the innermost parts of the accretion disk, what is called the inner hot flow. If it is like an atmosphere or a sandwich that is on top and on the bottom of the accretion disk, or even if it is the base of the relativistic jet that we also see in radio. So questions like what is the geometry of the corona, or even what is the typical size or scale, remain unanswered. So here I become a bit more technical in my talk. So because I need to introduce the technique that we use to tackle these questions, which is essentially what we call spectral timing. So in order to do spectral timing, we first need to explain what is timing. So when in X-rays we talk about timing, we are essentially talking about the Fourier transform. So as I told you, these sources, particularly in the hard states, are very variable. So when I say very variable, well, this means that when we create a light curve with, as you can see, just a couple of seconds, we see that the lighter oscillates a lot. The source oscillates a lot at very different, many different frequencies. So one usual way of studying this is to convert this information, which is essentially aperiodic, into the frequency domain, from the time domain to the frequency domain. And for this, we use the Fourier transform. And when we do that, we find that there is essentially some broad component with ranges many decades for the variability. And there are also some narrow peaks, some particular frequencies, not strictly periodic, but some more narrow components that encode some information about certain timescales, which are relevant. So these relevant timescales, or these narrow components, are called the quasi-periodic oscillations. So they are not periodic, but quasi-periodic, right? So there are these quasi-periodic oscillations come in with different names, with different flavors, and their shapes, let's say, or their properties in the power spectra depend on the state. So when we are in the low-Haar state and the intermediate state, we tend to see what the so-called type C QPOs. When we go into the transition, we see type B QPOs, where you can see that the main difference is that there is almost no broadband noise accompanying this narrow QPO, contrary to type C. And then when we go to type A, well, sometimes, not very often, we also find some very broad, quite broad QPOs, the so-called type A QPOs. So this is a bit of like the jargon we use in the field, but I need to introduce it. And interestingly, when the source experiences this transition between the two states, also things happen in the radio band. What we used to find is that when the source in the X-ray side, let's say it's in the low-Haar state, and the variability is large, we tend to see what is called the compact jet emission from a compact jet in the radio band. And when the source transitions to the soft state, we find that in the soft state there is no compact jet, but before this happens, there are ejections of relativistic blobs, which are we call it the ballistic jet or the relativistic jet, which is, instead of being optically thick emission, is optically thin. So people has been proposing several ideas to explain the origin of these QPOs, but mainly focus on the so-called dynamical origin, which is essentially the question is where the frequency of the QPO comes from. And well, as you can see here, an incomplete list of models. There are ideas connected to length theory precession in the innermost part of the accretion flow. The precession of the inner disk or the corona has been proposed for the type C QPOs, while the jet precession has been proposed for the type B QPO. There are different ideas connected to oscillations or instabilities in the disk, and other ideas which try to connect the system, like a natural frequency in the system that is made by the interaction between the disk and the corona. But in any case, I want to point out here that QPOs are very important because they indicate relevant timescales in these systems. And moreover, when the QPOs are strong enough, I mean in terms of data, when the significance that with which we can measure them is strong enough, then we can split the information thanks to the way that X-ray astronomy works. I'll explain that in a minute. And we can then measure energy-dependent amplitudes and delays that are encoded. Basically, they encode physical and geometrical information from the source. And this is just because of the way that X-ray astronomy happens. Because in X-ray astronomy, we detect essentially individual photons. And for each photon that we detect from the source, we can measure the time of arrival with high precision and the energy of the photon with relatively good precision. And this means that we can split the information that we have from an observation into multiple energy bands. And we can, for instance, study how important is a QPO in the hard band, in the soft band, in intermediate bands, etc. So when we do that, or when people does that, essentially what we find is that QPOs tend to be more important in the high energy bands than in the low energy bands. So the amplitude of the QPOs increase with energy, which somehow tends to point to the idea that the Comptonization process must be playing an important role in shaping the energy dependence of the process, because contrary to the accretion disk, Comptonization is important in the hard energy band. So we can do a bit more with this technique because, well, as you know, if you just take a certain time series, make the Fourier transform, and do this kind of play with the complex conjugate, you can get what is called the power density spectrum, the power spectrum as usual. But since you have different, in X-rays, you can have different energy bands simultaneously, you can have different time series at different energy bands. So you can also cross-correlate them or make what is called the cross spectrum. So when you do the power spectrum, essentially you all know that you get all real numbers, even if this is a complex quantity and this is another complex quantity, since it is the complex conjugate, then you get real numbers here. But when you do it with different Fourier transforms for two different time series, then you get complex numbers as a result, right? And these complex numbers encode two kinds of information. One, here in the absolute part, you encode the amplitude of the power, the cross power between the two energy bands. And here you have the phase, and the phase essentially encodes a delay between the two time series. So if we want to put it more easy, let's think we have two time series like this. One is the red band is the soft energy band, the blue one is the hard energy band. And you can see here there are two properties that are encoded here. So one is that the red has a lower amplitude. So when you put it now in amplitude versus energy, you get a small amplitude for the red and a big amplitude for the blue, right? But there is also something else. As you can see, they both seem to oscillate in the same way, but the blue one is happening a bit later than the red. So when you do the cross spectrum, you also get this information. There is a lag. There is a delay between the red photons that come first and the blue photons or the hard photons that come after. And in this case, it's the opposite. So one simple idea of how can we produce hard lags? Well, one possibility is that there are fluctuations in the accretion disk, and these fluctuations go to the corona, and in the corona, there is an inverse Compton process that happens after. And then once we see all the system all together, we can see that the same variations that we see in the accretion disk occur in the corona a bit later. So then you have hard lags. And how can we create soft lags? Well, in the opposite way. Part of the photons that are scattered in the corona have to come back to the accretion disk because they are emitted essentially isotropically in the corona. So they will produce echoes in the accretion disk or even thermalization, and this will produce soft lags. The variability in the disk will happen after the variability in the corona. So this is like a simple picture where you only have hard lags or soft lags. But when we go to reality, also these kind of things happen. So now if we have many energy bands, like we have measured the QPO in different energy bands, we can see here is the amplitude of the oscillation. Let's take this part. Okay, we plot it like this oscillation with this amplitude and this lag. And then when we put a second energy band here, we can see essentially this, that it's increasing in amplitude, but also there is some delay there. These photons are coming after. So the blue curve is a bit later than the other. If we go to the last band, then it's the same. So one could say, okay, everything that we are seeing in the 2 to 10 kb band, which is essentially the band that is covered by most time emissions because they use proportional counters, which is a way of detecting X-rays. Then everything is hard matched, so it must be something like Comptonization or propagation or fluctuation from the accretion disk to the corona. But then we had, in 2020, we had the NICER instrument also observing this kind of sources, and the NICER instrument is built a bit different, and it can cover also the soft energy band. And when we went there, we found something that was unexpected at the time, which is that instead of continuing having hard lags like this, no, this curve inverted, and there are now soft lags. So the same QPO, the same source, same observation is showing both hard lags and soft lags at the same time. Right? Okay, so given this, we came with some idea. The motivation is, okay, if most of the variability is occurring in the hard energy band, as we can see from here, then comptonization must play an important role for sure. So let's forget for all the other processes, and let's study how the comptonization varies, and if we can try to explain what we observe here somehow. So when we came with this idea of a variable comptonization model, the model, it's simple. We have an accretion disk and a hot electron corona, and then photons from the accretion disk go through the corona. Some of them escape, some of them feed back to the disk. They come back, they return to the disk, just because in the corona the emission is isotropic, so part of them have to come back to the disk. So sorry for the math, I will be very fast here, but essentially, in order to solve this problem, one needs to solve the components equation, which is the equation for comptonization. So the equation for the diffusion of the energy of the photons in the electron cloud. And what normally we tend to do when we talk about average spectra, stationary spectra, is we take this part and we say, okay, there is no variation in time, so we need just to solve this. And this is what leads to common models like NTH-COM, for instance, which is very used in our to fit spectra of these sources. But what happens if we don't make this zero, but we just allow it to vary? Well, there will be also variations in the diffusion of the photons in the cloud. So there are two terms here which are important. One is we need to inject photons to the Compton cloud. We do it with a spectrum of a black body or this black body. And then there is another part, which is the photons, which are the photons that escape. And those photons are the ones that we observe, that made the spectrum that we see. So next to it, we need to, what we do in the model is to propose that the physical magnitudes of the system oscillate at the QPO frequency. So there is a temperature for the disk, temperature for the coronas, and the heating rate. And then the solution that we get from there is an oscillating spectrum. It's an spectrum which is made from complex numbers. Essentially, the steady state is NTH-COM, like the typical Comptonizing spectrum, time average. But then we have these amplitudes, these complex numbers, which encode the amplitudes and the phases of the variability. So sorry, I will go on the, yeah. So the solution of the model is something like this. If you take the steady spectrum, it will be like the blue part here, the typical Comptonizing spectrum. But then if you allow it to oscillate, it will oscillate like the red line. And if you stand at a certain energy, for instance, here you can see the oscillation is small, while if you stand at this higher energy, the oscillation is larger. So the amplitude of the oscillation in this case is increasing with energy. And then there are also delays, because when you get the maximum here, you get the minimum here and the opposite. So there are delays naturally introduced in the system. And the model has essentially many parameters which are the same parameters that one needs to fit the time average spectrum, like the electron, the corona temperature, the optical depth, or the temperature of the disk. But then there are also parameters which are related to the geometry of the corona, because one needs to set up a corona size and also the fraction of photons that come back to the feedback. So, and so in a certain way, this model will allow us to estimate the size of the corona, which is the main reason why we do this. And also something about the shape in such a way that if the corona is, for instance, over the disk, like in a sandwich configuration, then we expect a maximum feedback or fraction or feedback, right? Because the corona is really extended on top of the disk. There are many photons that can come to the disk. While if the corona is elongated along the vertical axis, perpendicular to the accretion disk, then we expect that the feedback fraction finds a minimum value. Right? Okay, and in this way, since we have Comptonization, we can create hard lags, and since we have also feedback to the disk, we can also create soft lags from the model. Okay, well, this is just advertisement that the model is fully public and it's maintained in a GitHub repository, but I will fast here. Okay, and since we proposed the model 4 years ago, we have been studying many QPOs that in different outbursting sources that were occurring in these last years. Essentially, mainly thanks to NICER, who was observing these sources in a very dedicated way, but also thanks to the legacy from RxTE, an emission that is gone since more than 12 years ago, but it was a satellite designed to do spectral timing. But also satellites like NewStar, AstroSat, or HXMT, and essentially covering from 0.3 to 100 kV, so 2 decades, almost 2 decades in energy. So let's focus on just 2 results. Yeah, okay, I have time. First, let's go to the type CQPOs in 1915. Okay, I've become more technical now, sorry for, but 1915 is one of the archetypical microquasars that it was the first source for which the relativistic jets were actually discovered in the 90s. And since it was active during the 90s and even until just a few years ago, then it was observed during the 14 years that RxTE was there. So almost every day, we have data from almost every day during 10 years, more than 10 years, from both RxTE, so in the X-ray band, but also in the radio band, because in radio observatories like the Ryle telescope was also observing it very, very often. So Liang Shang, collaborator now based in China, he took all the legacy, more than 1,000 observations of 1915, and looking for QPOs in the source. And he found that there were more than 400 observations of RxTE having coincident radio data and showing type C QPOs. So he analyzed the 400 of them, a lot of work, and essentially found the interesting result, which is that the lags can be either hard, flat, or soft, depending on the QPO frequency. So essentially, when the source is below 2 Hertz, you see at 2 Hertz, it's essentially flat with energy. But when it is below 2 Hertz, the lags are hard, and when the source is above 2 Hertz, the lags become soft. They change completely. So this was at the time when I was a postdoc of Mariano Mendes in Captain. We had all these data set there, and we said, okay, we have the model now. Let's see what we found when we fit it. And it wasn't easy because we had to fit 400, and the model was not fast at the time. this was before we published it in GitHub. Now, if you download the model and you want to make in any laptop a realization of the model, it takes less than a second. But at that time, doing a realization of the model was about 1 minute. So fitting 400 observations was not an easy task. You had to build very big table models and then fit the data. But we managed to do it. We found this interesting result. So let's concentrate on the most important parameters. On the one side, the feedback fraction. Well, we found that something that was somehow expected. When the source was above 2 Hertz, since the lags are solved, we found essentially a lot of feedback between the corona and the disk. While when we were below 2 Hertz, when the lags are hard, everything is dominated by Comptonization. There is almost no feedback. So feedback has to be below 30, 40%. On the same time, we also were fitting the temperature of the disk from our model unit without looking at the spectrum. And when we did that, we found that above 2 Hertz, the temperature of the disk needed to be around 1 kb, so very hot disk. While when the source moved with the QPO below 2 Hertz, we found that the temperature had to be very, very low. And this was without knowing the spectrum of the source. But then we went and looked and fit all the 400 spectra of the source also. And we found essentially something very similar. We found that when we were above 2 Hertz, we could measure the temperature of the disk and also the disk flux, which is colored here. So you can see that there is essentially a contribution from the disk with a similar temperature to the one we found from our variability model. And then once we crossed 2 Hertz, we started to find that the disk was not contributing to the spectrum anymore, which is, given that this is RxD data with above 3 kb, this is essentially what you predict when you have either no disk or a disk with a very low temperature as the one that is predicted by our model. So there was both things fitting different aspects of the data work in the same way. So the other thing we could measure from our model was to determine the size of this Comptonization component of this corona. And what we found is that essentially when the corona, the QPO frequency is high, we find coronas of sizes between 100 Rgs that was essentially collapsing down to order 10 Rg at 2 Hertz. And then when we go to lower frequencies, the corona size, we found that it was increasing up to even 1,000 Rgs. And this was a bit debated in the literature, but a few years later, people from studying reverberation or like echoes in the source found a similar. They only did that for this source in one particular observation because they did this with newer data from NICER, but they also found let's say about 100 Rgs in corona size or corona height for these echoes. And yeah, there is something else that we found in this work, and it's mentioned here, is that in this part of the in this part, when the QPO is large, the corona tends to be the radio emissions tends to be quiet, while when the corona was below 2 Hertz, always the emission is radio loud. And you can see this across many years, 12 years of information. So the red is the QPO frequency. So almost every time the QPO frequency is red because it is above 2 Hertz, right? While at some particular points, you can see here, there are blue points when the QPO crosses below 2 Hertz. And if you look now at the greenish curve below, that's the radio light curve across the 12 12 years. And you can see that every time there is a big flare in radio is when the QPO goes below 2 Hertz and the lags become hard. So there seems to be a connection between the QPO lags in the X-ray band and the radio flags. And if you now plot the QPO frequency against the radio flags, you find that most of the points across 12 years, 400 of observations follow this branch, where you have no radio flags when the QPO is above 2 Hertz and a lot of radio flags when it goes below 2 Hertz. So we came up with this interpretation that the delays turn hard, so here, when the radio emission is loud, and this also happens when the corona drops in temperature. And this is when the radio jet is somehow launched. And when the radio jet is launched, we find that there is essentially no feedback to the disk. And that explains why the lags are hard. And on the contrary, when there is no radio emission, so there is essentially no jet, we find that we also know that the QPOs show soft lags. And these soft lags can be explained by a lot of feedback. So this means that now we have a huge corona that is on top of the disk and is producing a lot of feedback. So the corona is somehow changing in its geometry, also following the QPO frequency. Yeah, okay, so the idea is essentially plotted here. There is one part when the QPO frequency is large, where we have the corona as the inner hot flow on top of the disk. And then when the QPO goes below 2 Hertz, then we have a corona that is more like the proper jet, and there is no feedback with the disk. So let's now focus on enough time, state transition. So as I showed you before, we had this very nice observation on 2020 of the first QPO that was very well measured with NICER, having this coverage down to below 2 kb, where the lags can be hard and then soft in the same observation. So we tried to fit our model, and we did that. And as you can see, essentially the model covers what we see in the data, the trend of the data. We find that the QPO increases in variability with energy, and also we find that with a relative 40% of feedback, we can have both at the same time, the soft lags and the hard. But the fit is statistically very poor. So we came with this idea, which is, okay, let's see if we have enough room here to accommodate a 2-component corona, right? So the problem here is that when you go to X-ray data, normally we're used to add models like in expert, for instance, we put the power law, we put the black body, we put the reflection model. We just need to add things, or sometimes we have to multiply it by the absorption, for instance. But here we are talking about results which are in the complex Fourier plane. So the addition of the 2 coronas, we have to do it in the complex plane. So what we did is create another model, because we couldn't do this like in a typical fashion, which is a model which adds the 2 corona components. And we came and fitted to the data, and we found what we wanted, which was a chi-square below 1, right? So we have a very good description now of the data, of the QPO. But for this, we needed 2 corona. One corona is a small corona of about 10 RGs with a lot of feedback with the accretion disk, and another corona which is very elongated with very low feedback. So we came up with this interpretation. Like, we have 2 components. One is essentially the inner hot flow that many people talks about, which has a lot of feedback with the disk. And then the other is essentially the base of the outflow or the base of the jet, which has almost no feedback. And this was for us very nice, because at the same time when we were observing this type B QPO in the X-ray band, this type B QPO during the transition was coincident with radio jet ejections observed by the neutron collaborators. So this idea somehow fit in this scenario. And then we came and we started to look at other type B QPOs in other sources, like 1535, 1820. And we were finding that every time there was the kind of a similar phase lag spectrum, right? With this U shape. So of course, when we fit our model, parameters can vary a bit, but the scenario is essentially always the same with this picture. But let's focus on the type B QPO or of 1820, because okay, we have this U-shaped spectrum for the type B, but if you go to the observation in which this type B QPO was detected, one can go a little bit below, so half day before, sorry, and we find that during this part there was a type C QPO. So the source here was still in the hard intermediate state, and it was crossing the transition to the soft intermediate state, showing the type B QPO. So when we go and look what is the spectrum of this type C QPO, we find some interesting differences. So the type B has this soft lag, as you can see here, while the type C shows almost no soft lag. So the difference here is huge. It means that if we fit our model, we should find something different. And this is, so low resolution, sorry. This is what we found. So for the type B, the scenario is the same we had before. But now if we go to the type C, we find that both coronas need to have some feedback with the disk. So there are like a small corona that is the inner hot flow there. And then there must be another horizontal extended corona on top. That is the one that will be converted here into the vertical one. So, well, we had this. So before, here you have time, you can follow the size of the corona, which is increasing, the black one here. In the dashed line is when the source transitioned and the radio jet was emitted, the blocks were emitted, and here is a radio jet a bit after, when it became the maximum. And you can see that just during the transition, we had the conversion from this geometry with a small corona and a large corona on top of the disk, that then converted into the large corona, now vertically extended, coincident with the jet ejection. So before finishing, let me put a bit this result into context. A bit before, there was a Nature paper by Erin Cara, where using reverberation, a reverberation method, so looking at reverberation echoes from the corona on the disk, they could measure how the corona was evolving in time. And they found that during this part of the evolution, which is kind of a plateau here, the source, the corona height was essentially decreasing because the delay in these echoes was also decreasing, right? And the sizes that were estimated for this corona were of the order of tens of RT. But so people was expecting very, very small coronas at that time. But then this same source, 1820, the same that I showed you before with our results, here this part of the study was here in this plateau, but then the source started to go down and then went up again and did the full transition to the soft desert. And if you follow these points and try to estimate now the size of the corona through the reverberation echoes, you also find that there is an increase in these delays. And then the size of the corona was just of the order of tens of RGs in this part of the diagram. When it experienced the transition, it was also increasing, and up to even 500 RG. So quite similar to the results we found. But this was only having one echo and without fitting a proper model. Then in 2023, Matteo Lucchini and collaborators tried to fit a proper model for the reverberation. It's called RailRuns, and it's also a public model. And they found that in order to fit the data from this source, they needed to have like two coronas producing the echoes. One, a small corona of about 20 Rg, which was basically the one leading to the spectrum that we observed. But then there was also need for a very high component producing longer echoes, which is the one that produced mainly the lags. So it's essentially a very similar picture to the one we have to a variable Comptonization with QPOs, which is a different technique. So I think I'm running out of time, so I will leave essentially here my takeaway messages and leave the space for questions. Thank you very much.
Okay, thank you for a very nice talk. Are there any questions? Here online, yeah.
So thanks, Fede, for the review on all this topic that I had almost forgotten. I remember during my times working in this kind of things that one of the questions was the size of the corona that you touched a little bit. But I remember at that time were the hard lags, and there were a couple of sources in where we were finding like very long in terms of seconds, like 0.1 seconds, even close to half a second, hard lags. And at that time, we were questioning whether this could be explained by the Comptonization process, given that the size of the corona with those lags was huge. I don't know if you can comment on that, if there is new development. Or...
Yeah, well, that's a absolutely fair question, and I think the same kind of question remains, because both for hard lags or for soft lags, if what we find with models, let's say variable Comptonization models or this kind, all these models, what we think is the origin of the delays is the light travel time, let's say, essentially. So if you have a delay of half a second or a second, then it means you have 300,000 kilometers, right? Exactly. And if you take into account if you convert that into relativistic arches, radii, gravitational radii, you will end up with thousands or even 10,000s. Yes. And essentially, we find the same. We find big sizes, as I show you in different pictures. But it's also the same in the case of reverberation lags. So because there we are talking about hard lags only. But when people tries to fit these kind of models or of echoes, this means that in the data you are finding soft lags, and those soft lags are also large enough in order to need these 300 Rgs. So even if you put just pure Comptonization, or if you and you fit it to the QPOs, this is what we do. Or you go to the broadband noise, which is what this kind of study do. They take the broadband noise, they ignore the QPOs, or they take up observations without QPOs, and they measure soft lags in those cases. And for the same part of the outburst, this is essentially the same. We were observing, these are almost the same observations or almost the same day. There is also, if you look at, so if you have a model that depends on light travel time, you find consistent results. So, but the other possibility would be that these delays come from another, they are originated in a totally different manner. For instance, they could be originated in the viscosity. So viscosity could make them, if the viscosity is slower speed, then you need smaller sizes to get this proper. But then the soft delays that you measure here should also be explained somehow. So with the viscosity, I think you can explain hard lags because you have propagating fluctuations. People propose propagating fluctuations through the disk, and everything goes from a softer part of the spectrum to a harder part of the spectrum. But then you need also to explain the softness. Yeah, so I think the question, as I said at the beginning of my talk, remains open, and people in our field continue discussing what is the size of the corona and what is the geometry. And what I showed you here is what we get when we use like a physical model, simplistic as I showed you, which can be really more. It could be more complex, but we need also better data in order to test it. Yeah, this is. But also puts other part of the information into context, like also the radio data in the transition, or what we learn from there, right? So there is no definitive answer in this. Yeah, but they also lead to large corona sizes. Yeah.
Okay. Are there any other questions here or online? No? Okay, well, if not, we can thank the speaker again.
Thank you. Thank you very much.
And yeah, any PhD students come here and we can check that you're